Welcome back to Chapter 1. Let's talk about classifying matter in chemistry. So if you remember from Video 1, we talked about how matter is anything that's made up of particles. Another way of defining matter is that matter is anything that has mass and volume. And so to have mass and volume, it would have to be made of particles. So it really is the same definition, just kind of different ways of saying it. When we're talking about matter, though, it's not terribly useful to just say, look at that matter over there. It's really not very specific and kind of useless to us. So we need ways of classifying matter, ways of talking about the different properties of matter. And there's three very broad ways that we can classify matter based on their properties. And these are the state of the matter, solid, liquid, or gas, the composition, so what is present in the sample, and then the structure, so how the atoms are arranged in the material. So when we're looking at the phases, the physical states of matter, each of these different states are going to have different properties, and they're going to be very, very different in some cases, and sometimes they're kind of similar, but they are all definitely going to be different in one way or another. So solids, for example, have a rigid shape and a fixed volume. So these atoms are bound in fixed locations. They're not moving around. They are stuck in the crystal where they are. There are two less specific, or two subcategories, I should say, of solids. These are crystalline solids and amorphous solids. Crystalline solids are very, very ordered. Every atom has a place to be. There is a repeating structure in the way that the atoms are arranged. Amorphous solids, on the other hand, have no long-term order. It's just a big mess, essentially. Plastic, excuse me, plastics tend to be amorphous. Some of them are crystalline, but a lot of plastics are amorphous. It's just big long chains of carbon and hydrogen that are just kind of all wrapped around each other. There's no structure to the solid at all. Now that does not mean that it's not solid. It is still solid, but at the atomic level, there's no repeating structure. Liquids, on the other hand, have an indefinite shape, but they still have a fixed volume. So they're not expanding or contracting. You can't take liquid water, put it into a compressor and smoosh it down to half the volume that it started. That's just not going to work. It's not going to happen. You'll break your compressor. These atoms are still very much in close contact, just like they are in a solid, but instead of being in a fixed location, like they are in a solid, these can move around freely. So they're bumping into each other, and they're really close, but they're able to move. They're able to go wherever they want, and this is why liquid flows the way it does. You can shake the liquid, and everything kind of jiggles around inside there. It's because all the atoms themselves are actually able to freely move around. And so because of this, they assume the shape of the container, up to the volume that they occupy. They're not going to expand to fill the container, but as much of the volume as they can occupy, they will take that shape of whatever the container is. Gases, on the other hand, are both indefinite in shape and volume. So a gas will, in fact, expand to fill its container. If you have a container that has a vacuum pulled on it, so there's literally nothing inside of there, and you shoot just a little bit of gas into that container, that gas is not going to all congregate over in one corner of the container. It is going to expand to equally fill the container. Now, this does not mean that it's going to be like breathable air at that point. So if you shoot just a little bit of air into a container that was under vacuum, it's going to be extremely thin air, but it will evenly fill the container. Gases are just freely moving around in space, in the air. They're just freely moving around and bumping into things and bumping into each other and bumping into the walls of the room that you're sitting in right now, bumping into you. Gases are just freely moving around. And unlike the previous two phases of matter, you can compress gas, which I'm sure you've done many, many times. If you've ever taken like a water bottle that's empty, and you put the lid back on it and you squeeze it, and it pushes back against you, you are compressing the gas in that container. You compress it as much as your grip strength could do, and that was compressing the gas inside of there. The last phase here, which is one that we don't normally think about, but is actually the most common phase of matter in the universe, is plasma. This is for lack of a better descriptor, it's a very, very hot ionized gas. Now, calling it a gas is like saying that a liquid is a hot solid. They are very, very different in terms of their property, but there's just not really a better way of describing it. The reason why this is the most common phase of matter in the universe is because stars are made of plasma. So our sun, if you remember from The Lion King, there's the hilarious scene where Timon and Pumbaa are looking up at the stars, and Pumbaa says that he thinks that they're these giant balls of flaming gas, I think is the phrase that he used. And Timon is like, haha, that's hilarious, everything's gas to you. And the joke was like, oh, he was actually right, they are flaming balls of gas. And like, actually they're flaming balls of plasma. Which I guess is close enough for a kid's movie. So this is very, very high temperature, thousands of degrees Celsius. Lightning is another example of plasma. So the very, very high voltage that's released, the very high amounts of energy that are released with a lightning bolt, it's enough energy to actually convert the atmosphere to plasma where the lightning bolt travels. So what you're actually seeing there, that flash, is not actually the electricity. Like you're not seeing an electric spark there. What you're seeing is actually the atmosphere turning to plasma for a split second and giving off a whole bunch of light and then cooling back down. So you're seeing the effect of the electric charge being transferred, but what's actually giving off the light is the plasma. Right. So, moving on from that, another way of classifying matter is by either classifying it as a pure substance or a mixture. And we can take that a step further, and we can separate out pure substances into either elements or compounds, and the mixtures into either homogeneous mixtures or heterogeneous mixtures. So we have two large subcategories, and then each of those have their own two subcategories here. So when we're looking at pure substances that are elements, these are going to be things where the only thing in the sample, the only particles in the sample, is one element from the periodic table. One of the things on the periodic table that is the only thing that is present in our sample. That would be a pure substance because we have only one thing, only one kind of thing, and that one thing that we have is an element. And so that would be a pure substance that is an element. We can also have pure substances where we still only have the one thing, but that one thing that we have is made up of multiple different kinds of atoms. So we could have a pure substance that could be separated into simpler substances. You could break it apart into different atoms. So water is an example of this. If you have a sample that is pure water, that is a pure substance because the only thing you have is water. The only thing you have is H2O. But because H2O has hydrogen and oxygen in it, that's not a pure substance that is an element, because it has multiple elements present. That is a compound. If, on the other hand, if we were inside the Goodyear blimp, it is filled with helium. Helium is an element from the periodic table, so that is a pure substance that is an element. When we're looking at mixtures, so this is something where we have more than one thing in our sample, we need to ask ourselves, is that mixture uniform throughout? So is it the same everywhere in the sample? If it is not the same, everywhere, that is a heterogeneous mixture. So a heterogeneous mixture would be something like wet sand. If we were to go to the beach, scoop up some wet sand, it would separate to where we had sand that was wet at the bottom, and then we had water on the top. So we have multiple things present in our sample, and it's not the same throughout. It's not evenly mixed, essentially. If, on the other hand, it is uniform throughout, this would be a homogeneous mixture, and tea with sugar would be an example of this. Really, pretty much any drink that you ever have would be an example of this. So tea with sugar, you have the water molecules, you have the tea leaf molecules, you have sugar molecules if you take your tea with sugar. So you have multiple different things present, but it is uniform. If you take one sip of the tea, it's going to be the same, it's going to taste the same as the next sip, because it's the same throughout. It might be a little bit cooler, but we don't care about temperature when it comes to mixtures. Alright, so go ahead and pause the video for a second and see if you can work out what these 6 things will be in terms of those 4 classifications. Are they an element, a compound, a heterogeneous mixture, or a homogeneous mixture? So we'll take a look at these and then we will call it for this video. So go ahead and pause the video now. Alright, I hope you paused the video there and tried to work out what each of these are going to be. So that first one there, coffee, specifically this cup of coffee, and the reason I say specifically this cup of coffee is because this is fairly obviously just black coffee. It is not one of those fancy Starbucks drinks where, you know, everything is swirling around. They draw a pretty picture on the top and everything like that. It is just plain old black coffee. This is a homogeneous mixture because all of that solution is the same everywhere. There's not one part of the drink that's different than another, unless you had a really bad barista and they got coffee grounds in the bottom of your cup, which, ugh, gross. I don't like coffee in the first place, but then to have coffee grounds in it, ugh, nasty. So that would be a homogeneous mixture. Now, if it was one of those fancy coffee drinks where they drew a picture of, I don't know, Harrison Ford, and in the top of the coffee or something, then that would be a heterogeneous mixture because it wouldn't be the same throughout. What about brass? So brass, which is this here, is a little bit of a toughie. So brass is not something from the periodic table. If you went to your periodic table to see if you could find it there, it is not on the periodic table. If I remember correctly, brass is a mixture of copper and zinc, I believe. I believe it is copper and zinc. And so that would leave it as either being a compound or a homogeneous mixture. And this is, again, a bit of a tough one because it might seem like it should be a compound, but technically speaking, alloys, so mixtures of metals like this, are considered homogeneous mixtures. So that one is a bit of a tough one because there is a bit of technicality there. What about seawater? So seawater really has 2 different options, and it depends on what popped into your head when you read seawater, because truthfully it matters where you get your sample of seawater. If you were out in the middle of the ocean, away from everything, and you just took a cup and you scooped some ocean water up, that sample of ocean water would be a homogeneous mixture. It would not be a compound, and it would not be an element, obviously, because even just the water has more than one type of element in it. But that specific mixture would be a homogeneous mixture. If, on the other hand, you didn't get your sample of seawater from the middle of the ocean, maybe you were on the beach in, I don't know, Corpus Christi. I think Corpus Christi's on the ocean. And you just walk into the surf, 2 feet, and you take a scoop of some water from there. That is most likely going to be a heterogeneous mixture because you probably didn't get just water and salt, which would be what most people would think of as seawater. It would probably have water, salt, seaweed, maybe some scum, maybe a beer can, um, depending on how clean the beach is. Like, there's probably all kinds of different things, and that would not be a homogeneous mixture. If you have even the smallest little piece of seaweed in that mixture, it's not going to be homogeneous because that seaweed is not pureed into the sample. Now, if you took that and you did actually puree it, well then yeah, it would be homogeneous at that point. But just scooping it out of the ocean, it's not going to be. So that one is, again, it depends on where you took your sample from. So it's entirely possible that some of you thought homogeneous mixture and got it right, and some of you thought heterogeneous mixture and got it right. For examples of things that I will do on exams or homeworks or things like that, it should be pretty obvious. I will try to make it as obvious as possible. I won't do anything tricky to try and trip you up. What about gold? Well, gold, if you go and look at the periodic table, is one of the elements there on the periodic table. It is element number 79, if I remember correctly. And so because it is just gold, nothing else, that would be an element. So that would be a pure compound or a pure substance that is an element. What about this piece of marble here? So most likely, you either thought compound or heterogeneous mixture. Most likely. Those are usually the two answers that I get the most. Because marble is not an element on the periodic table. Sometimes people will say homogeneous mixture as well. But usually the two most common answers are compound and heterogeneous mixture. The correct answer is heterogeneous mixture. Now, if you're thinking, well, but it's marble, it must have a molecular structure. Yes, but there are lots of different molecular structures. And you can see that here because it's not the same color throughout. Because there are black areas and white areas and gray areas in between, the fact that the colors are different tells you that the molecules are different. So it is not the same molecule throughout. There might be some similar molecules, but they are not all the same. And so this would be a heterogeneous mixture. Anytime you have a sample with one area colored differently than another area, it is going to be heterogeneous, by definition. If it's the same stuff or it's evenly mixed, it can't have different colors. So then the last one here, salt, sodium chloride, it is a compound. So sodium chloride, NaCl. Some of you might have tried to get super technical and be like, oh, but table salt has, iodine in it. Not trying to be tricky here. We're talking about just salt, just sodium chloride. That is a compound. So if you did think, oh, he's trying to be tricksy and he's thinking of the iodized version, that would be a homogeneous mixture because it is evenly mixed. But what I was really getting at was just plain old sodium chloride. All right. We'll call it there for this video. In the next one, we'll talk about physical versus chemical properties.